Hello and once again welcome to my channel SST Chemistry. In today's organic spectroscopy video, we shall be discussing the proton NMR analysis of a very simple compound 1-bromo-2-methyl-butane, a comparison between the simulated and the actual spectrum. Now, 1-bromo-2-methyl-butane is a very simple compound, and if you are an undergraduate student, you will say it will show 5 proton peaks. One for this methyl, the other for this methyl, the third for this methylene, fourth for this methylene, and the fifth for this methine. So there will be 5 proton peaks. But actually, if you are a postgraduate student and have knowledge about stereochemistry of proton NMR spectrum, you will say there will be 7 proton peaks. Because this is a chiral center, these methylene protons are non-equivalent, so also these methylene protons are non-equivalent. They are called, as you know, diastereotopic protons. So you will get 7, 1, 2, 3, 4, 5, 6, 7 proton peaks. Now let us use the Sulleri rules from the table to predict the shift positions in ppm. Now this methyl will have a tentative shift positions nearing 0.9 ppm. And this methyl will have a peak position little greater than 0.9 because it is little closer to bromine. This methyl will be a doublet and this methyl will be a triplet. Coming to this methylene protons will be in the vicinity of 1.3, but there will be 2 peaks. These methylene protons will be in the vicinity of 3.3 because it has a directly bonded bromine atom. So 3.3, this the methylene. 2 peaks. And this methine, which is having a beta bromo, methine usually is 1.5 without any further increment, but the beta bromo adds 0.25, so 1.5 plus 0.25, that will give you the value of 1.7. So our predicted value is 1.75 for this methine proton. This is 0.9, this one is little more than 0.9, and this will be a triplet, and this methyl will be a doublet, and these two in the vicinity of 1.3, these two in the vicinity of 3.3, but the peak multiplicity pattern is very interesting. Let's first talk about this one. This methine proton will be an apparent octet because there will be 7 neighboring protons, 2 plus 3 plus 2, 7 plus 1 octet. But if the J values of these 2 protons is less than the other 5 protons, 2 plus 3, then it will be a sextet of triplets. So I have predicted this 1.75 ppm peak for the methine proton could be either a sextet of triplets or octet. And these two are very interesting. If one of them is a DQD, the other one is a DDQ. Supposing I have taken this, supposing this is at 1.3, the other one is at 1.37. So there will be 2 distinct peaks you will find in the actual spectrum. If this is DQD, doublet with a J2 geminal coupling of higher coupling constant, and then quartet with the J3 coupling, and still a lesser coupling constant with this vicinal coupling having a lower dihedral angle between these 2 protons, nearly 60 degree. So the prediction I have made here, these two peaks, if you see the real spectrum, what we predicted, there are 7, 1, 2, 3, 4, 5, 6, 7. This is the peak for TMS. This triplet for this proton 0.9, this doublet for this methyl at 1, that is easy to understand. But these two protons in the vicinity of 1.3, we are getting one at 1.3, 1.5 and other at 1.35. And they are two distinguishable peaks, no overlapping. And the spectrum has been borrowed from my friend Professor James Nowick from University of California or Irvine, and that is from the Aldrich chemical source, the most authentic, most reliable source. These are the two non-equivalent methylene protons in the vicinity of 1.3. Actually, one is 1.35, the other one is 1.5. I have predicted 1.5 to be a DQD and this one with a DDQ. Why? Because this is geminal coupling. I have predicted a value of 13 Hz, and this one, which is at a dihedral angle of 180 degree trans, will have a greater coupling constant than this J3, which is 6.5, and this is 8. Therefore, this is doublet of quartet, DDQ, and this will be a doublet of quartet of doublet, 13, 6.55. But you can also say each one will be a DP, doublet of pentates, because if the coupling constants are same, 3 plus 1, 4 plus 1, 5, and this is geminal, no doubt, nobody can challenge. So doublet of pentate, you can say each one is a DP, but I beg to differ. I never agree with DP. I will show you in simulation. DP will not satisfy the actual peak pattern containing 7 distinct lines, and each line you find you will be a finer doublet. Because of the printing, it has been smoothed out, but it is a finer doublet. And the possibility of a DP will be eliminated very soon. I will simulate the spectrum in your presence. And about these two protons, which is a part of a ABX pattern, ABX. It is a complex ABX pattern, and this is the AB portion. If one is at 3.30, the other one is at 3.37. Each one is a DD, doublet of doublets. This is a J2 coupling and this is J3 coupling. So each is a DD, but they are very close to each other. So complex pattern is being observed. There is a tinting effect. The inner lines grow in height. So you can't find two DDs of fast order nature. This is a non-fast order AB part of the ABX portion, ABX, right? So let us try to simulate in another package, Excel software. You find here, this is an Excel software package for simulating the peak pattern, giving the J values. You put the J values here, there are 5 J values, you get what could be the peak pattern. And I have given this for a DQD. This is the 13 Hz for the geminal coupling and 3 protons for the quartet, 6.5, 6.5, and the last one is again J3 for the lower value, the Gauss, smaller dihedral angle, 5. So it looks like there are 7 distinct lines, but each one is a finer doublet. This exactly matches with the peak I have shown you at 1.5. 1.5 I showed you is a DQD, and the other one is a DDQ. Here I put 13, this is 8, and this is 6.5, 6.5, 6.5. So you will find again the 7 lines. Each one is almost a finer doublet. So that also matches with the other one at 1.35. So, but if you make it a DP, this 6.5 and all are 6.5, it will be exactly, since 13 and 6.5 is exactly half of 13, there will be merging of lines, you will get only 7 lines. No doublet. Each component will not appear as a finer doublet. It will be a clean 7 lines. That is not, you are not getting. Even if this, supposing it is not half, it is supposing 12 and others are 6.5, you will get the middle peak is of lower height than the outer peaks. So this is, you are not getting, the middle peak is the highest one. So the possibility of DP is ruled out. Coming back to our work. So our prediction has been found to be very, very close matching with the actual spectrum. This is a triplet, this is a doublet, this is a DDQ, this is a DQD, this is an octet containing 8 lines, can have a loop from the here to here. There are 8 lines. This is a DQD, DDQ, cannot be a DP, and this is a DDDD at the downfield region. So everything is done. And I would like to also tell you, are you familiar with this software, online software nmrdb.org? If you are, then you can play with it, but it's not reliable at all. I will show you how, for a higher level analysis, these softwares are based on some rules. They do not give you the idea or the peak positions of the diastereotopic protons. They will give an idea. As an examinee, you can use, if you are allowed to have an idea to save time, but it's not reliable for research purpose. You see how unreliable the prediction is by using this NMRDB for the same molecule that we are discussing. See, I have already drawn this 1-bromo-2-methyl butane. It is showing these 1, 2, 3, 4, 5, just like an undergraduate student, 5 peaks. In the table, it is indicating there are 2 peaks at 3.157, 3.157, and 2 peaks at 1.155, 1.155. So it is indicating there could be 2 peaks, but it is showing only 1 peak and the multiplicity of 1 peak, and that too erroneous. Look to this downfield peak here, these 2. Maybe it is showing 1 peak. If you just highlight, it is showing a doublet. Instead, it should be a DD, doublet of doublets, with a geminal coupling of higher value and then vicinal coupling of lower value. It is showing only doublet, is writing also doublet with 1 coupling constant, and that to 6.65. You can't believe that geminal coupling constant will be as low as 6.65. And so also the vicinal coupling constant in other peak patterns will be 6.6, 6.5. So this is unacceptable. This should be DD. Oh yes, you cannot distinguish between the 2 geminal protons. You are not going to give the different shift values. Give 1, but you can't say it is D. It is DD. Similarly, this one, it is saying DP or doublet of quintets, as they say, but I used to say DP, doublet of pentet. It cannot be. I was simulating using the data J 7.14 and 6.5. You will not get those type of 7 lines with each line finer doublet. You will not get. So I showed you doublet of pentet can be either clean 7 lines if the second J value is half of that, and very interestingly, the geminal coupling has been shown to be 7.14. Can it be 7.14? Geminal coupling cannot be as low as 7.14 if it is not very close to an electron withdrawing group. Geminal coupling will be more than 10, 12, right? So these values are not at all reliable. Only triplet for 3 protons and doublet for 3 protons, methyl, but that also the prediction of the shift values are not matching with the actual value. rather our predicted from Sulleri rule are matching. And this is TH. I'm really wondering, what is TH? Is it triplet of hextet? It should be ST, sextet of triplets. And the J values it is giving will be almost an apparent octet. The J values are close and it will be an apparent octet, 8 lines. So, and the predicted J value is 1.69 against our prediction 1.75, but the real actual spectrum is also 1.75. So, you can, as a student, I always recommend to play with this. Just double click, you will get all the spectrum. Just highlight. This is the octet, 8 lines from here to here. And this one is only one pick is given as 5 lines. It is saying DQ should have 10 lines. It is saying it is 5 lines. These two are cool. So in actually here this will be 2 picks. One will be DDQ and the other one is a DQD. And this one will be 2 picks. Both are DD. So coming to the analysis we have done, there is very less matching between the predicted values in NMR-DB, that is simulated spectrum, and the actual spectrum. One cannot find the two values of the diastereotopic protons, just gives an idea. And the peak pattern recognition is often erroneous. The DP is not possible with the values. So we have predicted DDQ, the other one is DQD. And this CS2BR, the downfield peak shows a DD each. That means 8 lines. It is showing only doublet, not even 4 lines. So it is giving only one peak. It should be DD, not D. The suggestion is simulated spectra should be taken as approximate guide for actual prediction, not to be reliably used for assigning data values and recognizing the peak multiplicity patterns for real analysis. How did you like it? If you have liked, hit the like button, and also if you have not subscribed, do subscribe. We will be regularly producing videos for your interest. Bye bye.